Okay, go.
Oh, hello. My name is Antulio Gomez. Uh, I'm an aeronautical engineer, and I want to talk about the AG2 and talk about agricultural aviation. The AG2 was an airplane in which I had a big part in the design and build of the airplane, and I have intimate knowledge. I don't know how to say it, but to validate my experience, my familiarity with the airplane, I tell you right off the bat that the AG2 had a wing area of 321 square feet, a chord of 94.1 inches, and the airfoil section was the NACA 64021. That means that it was a big rectangular wing, about 94 inches in depth and a span of 42 feet. It's a big wing. And 21% thick airfoil meant that in the middle, it was like about a foot and a half thick. So you could have a lot of fuel and a lot of fertilizer liquid and so on. So it had a lot of advantages. Let me tell you more about the AG2 versus the first crop duster. The first crop duster was the Stearman, a biplane, a primary trainer in World War II. They were built by the thousand for the Navy and the Army. And at the end of World War II, they were available for a small price, $1,000, you could buy one. And then they began to use the Stearman as an agricultural airplane. They replaced the small engine that they have for the Pratt & Whitney R985. That was in the BT-13 during another trainer in World War II, and there were hundreds of engines, so they got a cheap engine and a biplane that was acrobatic, and it was ideal for crop dusting, to start a crop dusting application company. But it was not the Stearman was not designed for agriculture. It was designed as a primary training. So it was not the best, but it was the cheapest. The Ag-2, on the other hand, was designed specifically for agriculture. And we can justify the different things that were selected in the primary design because we were trying to come up with a product specifically useful for agriculture. Now, the original work was done in Texas under Professor Wyke, and they built an airplane called the AG-1. The AG-1 was an experimental airplane. It had the same platform and the same size as the Ag-2 that I became partly designer of. The AG-1 performed very well, and the characteristics were as follows. By having a thick airfoil like the NACA 64021, you had a very smooth stall. That meant that you didn't have a sharp stall like you have, for instance, in a primary trainer, like the Stearman that has an airfoil that was about 12% thick, and it would have a sharp stall. So the thick wing is better. You have better control during the stall. There are other reasons for having a wing like that. I would like to say some things about stalling. Most people have a technical reference on what the stall is, but I want to put it in my own words. A stall is an interruption of the airflow over the wing on the top, but it doesn't occur at the same time everywhere. In other words, if you have a rectangular wing, possibly the stall occurs by having an interruption of the airflow close to the root of the wing. If you have a trainer with a taper wing, Then the stall occurs where the ailerons are. You need the ailerons for the lateral control of the airplane, which is not a good idea, so you have to put twist on the wing. Well, all those things come into play. If you want to design a crop duster and you are flying, say, about 60, I would say, let's make 80 miles an hour, and you get to the end of the field and you want to make a turn, you don't want to make a turn like you see at the airport, where the airplane banks slightly and makes a turn. And what you want to do is to make a very sharp turn with the airplane half stalled and come back pretty close in line with where you started from. And that's called the crop duster turn. And it's dangerous, but at the same time, it saves time. And the agricultural pilots get good at it. And the Stearman is an acrobatic airplane, it can take it. And the Stearman has a light wing loading, so it works out okay. Now, that's a fact. The Ag-2 is primarily designed to make a turn in the stall, in the semi-stall condition where the flow gets interrupted, with an airfoil that is gentle, so you don't have a very sharp drop in the lift. And it had slots and things like that, and other devices to have good lateral control, like spoilers. And you could make a very safe crop duster turn with a bigger airplane and so on. Well, that's essentially the story of the Ag-2. It was bigger than the Stearman. Roughly goes as follows. A Stearman was an airplane designed with an engine of about 300 horsepower. Later on, they put the R985 because they were able to get it cheap from the basic trainers, the BT-13. And that was about the maximum size engine you could put on a Stearman airframe. You put a bigger engine, you had trouble. And the weight of the Stearman was probably about 3,000 pounds, maybe 3,500 with the big engine. The Ag-2, on the other hand, we were able to put a bigger engine on the R985, the 450. We went to the R1340 that came from the T6 Texan. And it was double the capacity. It was a gross weight of 6,000 pounds, so it could carry more payload, more fertilizer, and that made it more efficient because you wouldn't have to be loading it so often. That's the first thing. Also, the wing loading on the AG2 was greater than on the Stearman, which meant that there was more downwash, more penetration of the grain or liquid fertilizer into the ground. So all those things versus very good control through a stall turn. Now, remember, I said that wings don't stall all at once. When you say a wing is stalled, it's because there are portions of the airflow on the top of the wing that where the flow separates. So in the Ag-2, on a stall turn, the wing wouldn't be stalled everywhere, so you would have good control and you could make a crop duster turn. What else?
The history of the plane as it was being developed and the economics.
Okay, the key thing, now I'm going to talk about the money thing, the situation. I would like to tell you that when I started working in the Ag-2, I was just an engineer right out of school. And I didn't know anything about agricultural aviation. But working with George Wing, the Transland Company, and the many years that I was there, I learned a lot. Now, this is what I learned. At the end of World War II, there was a shortage of food in many places around the world. For the first time, people began to use fertilizer and apply it with airplanes because airplanes became cheap by adopting basic trainers from World War II, modifying and changing them, all kinds of airplanes. They began to use for agriculture, and they began to use DDT, and the production of food increased. I'll give you an example. In 1949, when I immigrated to the United States as a foreign student, Mexico didn't produce enough food to feed itself. Actually, at the end of World War II, that's the way the conditions were. Mexico imported food. By the middle of the 1950s, the agricultural production of Mexico was 4 times as much, and it was exporting food, and all because they began to use fertilizers and airplanes. And so was all around the world. As a matter of fact, when we started designing the AG2, it looked like we were going to sell many, many of those airplanes. Remember, the AG2 was started about 1954, and it began to fly for the first time in 58. And DDT and agricultural aviation was expanding at full swing. What else I can say about that? But later on, people found out that DDT had unfavorable effects, and that put a big crunch on the expansion of the industry, and the Ag-2 just came too late. What else?
Did you mention why it had a bigger engine?
Oh well, the engine is an important aspect. You need to make a good agricultural airplane. You don't want a very fast airplane. You want essentially a slow airplane, very forgiving, and you want to have good control in turns so that you can make that crop duster sharp turn where the wing is half stall. What else can I say about that? The key thing in here is that you want an airplane that is aerobatic, that can take the G's on a turn. You want an airplane that is not very fast, so you want a light wing loading. You don't want to have a wing loading of 30 or 40 pounds per square foot. You want to have something like about 15, 20 or something of that order. I think the Ag-2 was a heavier airplane with a wing of 321 square feet, a weight of 6,000 pounds. You take 6,000, it was about 20 pounds per square foot, which was heavy for a crop duster. About the engine, the engine of choice in the beginning were small horsepower engines. The crop duster of choice was the Stearman. The Stearman came up with the Jacobs, or an equivalent engine of about 300 horsepower, 320, 350, something like that. When they start using it as a crop duster, on the other hand, you make more money, you carry more payload. So they went to a bigger engine, and the Pratt & Whitney R985 became available. Those engines came from the BT-13s, primary trainers, and they were very cheap. And the marriage of the R985 with the Stearman is what made the Stearman an ideal crop duster. It was cheap, it had enough power, it didn't stall, it had good characteristics doing the stall, and it fulfilled the slot very well. Later on, when we were designing the Ag-2, from the Ag-1, we went to the R985, the engine of choice. But then the engines became more scarce because more crop dusting pilots were using the R985, the 450 horsepower engine. So we went to the R1340, the 600 horsepower engine. They were cheaper than the R985, and it made the Ag-2 perform much better. Now, there is no if you go into the bigger engines, you have to go to much faster airplanes, and then they're not suitable for crop dusting.
Could you put an R1340 on a Stearman?
No,
No?
no way. He'll tear it apart.
Oh, okay.
That's 600 horsepower.
Mhm.
450 was the maximum. You put a bigger engine, and you can't even land it with maybe somebody tried it.
Uh-huh.
I'm sure that some of the pilots tried it, but
Mhm.
that's a big, heavy engine.
Okay, I was going to ask, did you want to talk about George Wing?
Well, if you ask me, the interesting thing about it is the different people that work in agricultural aviation. I don't know all of them. I know only the ones that work at with the George Wing company, the Transland company. I could talk about George Wing. George Wing started in North American as an engineer. He invented the high shear rivet, which I'll explain on another occasion. The high shear rivet became the primary choice rivet for highly stressed parts in airplanes during World War II, and it's what made the George went into business building high shear rivets for North American and then for the whole industry. That was the base. That was the money maker. George Wing always wanted to be an airplane designer. That was his ideal. And he wanted to get in aviation. And that's the way he got into agricultural aviation. One branch of the Hashir Corporation was the Transland Company, which specialized on all kinds of accessories for agricultural aviation, which means Stearmans. Everything from the hoppers to carry solids to the liquid delivery systems and so on for the Stearmans were built by the Transland Corporation. The Transland Corporation became the company that sponsored the building of the Ag-2 under George Wing's direction. He wanted to be an airplane designer like Donald Douglas or some of the other people. So he bought the rights to build the AG-1 from Fred White in Texas A&M. And that was the prototype of the AG-2, an airplane designed for agricultural aviation in an agricultural college in the United States. And it was a terrific airplane. But to build the AG-1 with the Lycoming 250 horsepower engine, that didn't make any sense. George Wing began to think in a bigger airplane, one that could be a competitor to the Stearman, and that's the way the AG-2 came about.
In how much of the AG-1 and AG-2 share in terms of
The
engineering?
aerodynamics, 100%.
Mm-hmm.
From the construction, the stress analysis, everything else was different. And the difference was not only was it a bigger airplane, but the AG-2 was certified by the FAA, and the FAA had requirements for regular airplanes. The AG-1 was an experimental airplane. It was never put in production. We built the AG-2 so we could manufacture thousands of them.
Mm-hmm, mm-hmm. Now, when you did the AG-2 as a prototype, what did you estimate its cost of production was in the 1950s?
Well, I was not in the loop in putting prices, but I can tell you this: building one of the prototypes probably cost $250,000. The engineering, just the engineering cost of the 4 years it took to build the AG-2, we spent about 20,000 man hours. I was an engineer, and I myself alone estimate I put about 4,000 man hours on that airplane. So it's expensive.
Uh-huh.
The predicted price for the AG2 was about $50,000. Now, let me back up. In the beginning, a Stearman, you could get it for about $1,000, but that was in 1946, 47. By the end of the 1960s, the price of a Stearman would be about $10,000 or $15,000. So the idea that you could build and you could actually get an Ag-2 for say 30,000, that's what the target was when we started building the AG2.
Mm-hmm.
By the time we finished and did all the work, we were thinking more like about $40,000 a copy.
Mm-hmm. Okay.
But that time, a good Stearman and good thing was more than 10,000, and they were not enough.
Mm-hmm.
And the thing was expanding. See, the agricultural aviation was expanding full blast all around the world.
And when if you took a Stearman side by side with an AG2, what would be the comparison in terms of how much of a crop you could cover on one versus the other?
Well, if you were to look at the two airplanes side by side, you could see that the Ag-2 was bigger, but not exceptionally, not much larger. The length of the airplanes were comparable, but the span of the Ag-2 was a great deal more. You could see it right off the bat in photographs. I guess what I can say is that the AG2 was an all-metal airplane. The Stearman was fabric covered biplane, and it came from a technology that was much older. I don't know. I cannot go ahead and say which is the better airplane. I think that the Stearmans were beginning to disappear from crack-ups and use, and something had to come in and take over and use them.
Mm-hmm.
In other words, the Stearmans were beginning to disappear. You could not get another one. Like they were not plentiful like they were in the 40s. By the end of the 1950s, a Stearman became to be the price was low, but you couldn't find one.
Mm.
And people were flying with spares, literally.
Wow. Okay. I think another question I had was that when you also spoke of another airplane company.
Yes, Grumman.
Grumman.
Grumman took advantage of it and came up with the they call it the Ag tractor, which almost is a copy of the AG2, except it's a little bit smaller, but it's using the R985 engine. And if you look at the two, they look very much alike. They make two planes, a biplane and a monoplane. And they copied a lot of the Ag-1 and Ag-2. Grumman is an excellent company. They don't need the help from us. But they did a good job. They were
Because
when Grumman could go on production on the Ag tractor, we couldn't. Grumman had the benefit of building airplanes for the Navy, and they had plenty of money in the bank. We didn't find the financing that was needed to put the Ag-2 in full production, even though that's what we decided for. So eventually the Grumman outlasted us and outproduced us.
And but one of the things I think you spoke is that by solving the same problem, you kind of ended up with similar airplanes. Is that true?
The airplanes look very similar, and the way you fly agricultural aviation hasn't changed.
Mm-hmm.
The key thing in agriculture is that you go on a field and you follow the crop, and when you get to the end, you have to make a very sharp turn and come back, almost in a lane parallel to it. So here's the problem: how are you going to do it? You could go ahead, make a pass, and make a long run all around, and then come back on the other side and make parallel passes. Well, if you're a good crop duster pilot and you got a very manual airplane, you learn to do the stall turn that crop dusters pilots often do, and make a lot of more money and be a lot faster. That's what the Ag-2 was designed for. And let me tell you, it was designed for that for two reasons. It had a spoiler. It had a slot flap. The NACA 2B flap was slotted, so that meant that when it went up, they increased the flow over the flap, so the flap wouldn't be stalled. The spoilers were designed so that they gave you favorable yaw when the wing was stalled. But let me repeat: when I say the wing was stalled, I don't mean the entire wing. That never happened. In airplane aerodynamics, when we talk about airfoils, they are essentially like two-dimensional pictures of what an airfoil is. And when the airfoil stalls, the whole airfoil looks stalled, but that's like if you had a wing in a wind tunnel and you were only seeing this thing. In an airplane, a real airplane, you have induced velocities and so on, so that the flow over the span of the wing is different at every point. So you're never going to get the entire wing stall at the same time. So when we say the wing stall, it means we lost lift, but we don't mean that we lost 100% of the lift. And that's where the airfoil becomes important. If you have a wing airfoil like the NACA 64021, it has a very gentle stall. It's not a sharp thing. So that means that you could have parts of the wing stalled, but it's gentle, and you increase the control during the stall, and that's what you need in order to maneuver the airplane and recuperate and come out of the stall flying and not crashing up.
So another question I had is, what did you think when you found out that the original prototype still exists?
You mean the AG2?
Yeah.
Look, I like to tell a story. That prototype, I walked around that airplane many times while it was being built. One of the tasks I had was to do the weight and balance. That meant that I calculated the weight of every nut and bolt and everything for that airplane. And as it was being built, I went and updated a file so that at any given time I could calculate the CG of the airplane as the airplane was being completed. The whole idea was that we had bounds. With the CG as we were building it, when out of those bounds, we immediately had to take drastic action to make it come back the way it was supposed to be. Otherwise, the airplane wouldn't fly properly. So that meant that I knew every part of the airplane, so that's the first thing. That airplane, I walked around it as the panels were taken out of the jigs and were assembled into position. And I saw that airplane fly for the first time ever. So we have a long history. The AG2 number 1, I never thought I would see it again. 2 of the Ag-2s that were built afterwards crashed. So I never thought that. I always thought that airplane was lost. What else can I say? I have pictures of it. Maybe you can see a picture of me working with one of the mechanics by the engine and so on. Yeah. Can I tell a joke?
Yeah.
since I was doing the weight and balance on the airplane, every time a component came out of the jig, say a wing panel, a rudder, a flap, there was a prediction of what the weight of the whole component would be, and we had a raffle. Well, one of the main panels, the outer panels of the wing, some of the heaviest one, was coming out of the jig, and everybody made a guess of what the weight should be. Now, my guess was my calculated value of how much that panel was going to be. I kind of forgot what it was, but it was like, say, I'm going to make a number, 211 pounds for this big wing panel. That's my calculated weight. And everybody else made different things. We'd take it out, and then we would weigh it. And then whoever got the closest one would win a pot of gold or anyway, it was a lot of fun. When that big wing panel came out of the jig and they weighted it, it was heavier. It was over 40 pounds heavier. Now that meant curtains for me. I was a young engineer. I couldn't understand how I could have missed the weight by that much. I was hoping that I would miss it maybe by half a pound or something like that. So I was very much alarmed. And I went running back to the office, right next to where they were building the airplane, and looking at my figures to see what the heck happened. Okay. And I could not find any reason why my calculations were that off. So I came back apologetic, worried that maybe I'll lose my job as an engineer. And everybody began to laugh, including my boss. Well, I knew there was something wrong somewhere. And then I found out that, unknown to me, in the loft group, they had some lead ducts. The lead ducts were used to make counters on the drafting table with plastic rulers that bend so you could make curves. They took the ducts, they put it inside the wing, they took the wing out, and they were having a big laugh on me. That I remember. I also remember one day at approximately 1 a.m. or 2 a.m., I had come back from work like about 8 or 9 p.m., and I was sleeping, and I got a call from Loomis. And I'll tell you who Loomis was later. But one of the workers there, the power plant group, called me. Said, Tony, we got it out. It's all put together into now. So I rushed and got into my clothes, jumped into the car, and about 4 a.m. I rushed down to Torrance, where they had a big hangar, and we had buildings and materials, and there was the Ag-2 all put together in not every bolt properly tightened, but the whole thing was together, and we never seen it. It was very, very nice. And then there was the first flight, and they started the engine, and the engine roared, and the test pilot went aboard, and the whole plant was outside watching the Ag-2 take off for the first time. And we all watched it go, accelerate, and make a liftoff, and go up in the sky, and flew for about an hour, made some turns and passes over everybody, and then it landed. And I remember everybody was happy. We have accomplished something. But when the airplane stopped and everybody went home, it looked just like another airplane on the field of Torrance. Made the same noise. and now it's all quiet.
Hmm.
The fun was building it.
Uh-huh. Yeah.
And then there was the flight testing. And all of a sudden, there were the stalls ones where you calculated the stalling speed of the airplane. And the numbers would be coming in, and people would be checking against the calculated values for the different gross weights. And then you had to modify the raw data for density and temperature and all that stuff and get it to standard conditions. And boy, my goodness, the calculations show that we were within half a mile per hour on the stalling. I don't know how we did it, but we did those calculations. Also, the top speed, and then the something called the VN diagrams. It's amazing. That is something like about 70 years or 60 years. One could calculate an airplane performance and hit it right on the money, all in 60 years.
Since the Wright brothers.
Yes. Building an airplane was no longer chance. It was essentially like building a building, like an architect builds a building or a bridge. Anybody can build an airplane if he knows the rules,
Mm-hmm.
and if he understands the science and follows the regulations. Yes.
Okay.
Yeah. Well, I got a lot of more stories, but I don't know where to start.